cloud. It looks like it's recording. Okay, sounds good. Oh, sounds good. Okay, okay. So let's get started. Does anyone have any specific topic in particular that they want to start with while I look at possible? Here, I think you guys are Alla students and Kong students. So if there's any specific topic you want to go over, feel free to let us know in the chat. I'll wait a bit so that everyone can like gather to questions. You got algorithms, number theory. I think because there's two separate classes here, it might be a bit of a mixture of both. But we'll be sure to go in order. Graph theory. Okay. Adjacency matrices, instance matrices. Okay. Graph theory, graph theory. Okay, let's do a bit of graph theory then. Um, got it. Okay. Graphs and graph models. Okay, let's just get started. Then- Okay. So is everyone let's actually just go through graphs in general. Is everyone okay with the notion of graphs, like the different types of graphs? You all want to go over that? Um, Anything regarding the directed graphs, regular graphs? I think these are, yeah, it could be the use of the graphs. Right, sounds good. So in that case, let's just go over everything and go in order. And whenever anyone has questions, feel free to um feel free to interrupt. Feel free to like if you want to jump to different topics, that's all good as well. In general, one of the big topics in 220 is graphs, right? So how do we know about graphs? We got this is usually the typical notation for graphs. You got G is equal to VE. V is the set of vertices. You could think of them as nodes, right? These are different, they're interchangeable words. Vertices and nodes are the same thing. And E are edges. So whenever you have a graph, it's a simple graph, right? So this is an example of vertex, right? And here's an example of an edge, right? So pretty basic, right? And we got um here's an example of graph. And the useful thing about graphs is that you'll see, especially when you go later on in your CS careers, that we as CS people tend to use graphs a lot. So here's one example of the use of a graph to represent a computer network between different cities. Each city is a node, right? And we can represent the connection between two cities with an edge. So this edge tells us that San Francisco is connected to Denver. Same thing for Detroit, New York, Detroit, Chicago, etc. Right? And these are examples of simple graphs, right? So then once again, we'll go into like different types. You'll also see here, LA Sarkar is requesting to record. You don't need to record this to your computer. I'm recording it to the cloud right now. So afterwards, you'll get a video of it. I'll show you where the video is. So I'm just gonna to the person trying to record. I'm gonna decline your record. I mean, yeah, should I decline it? Yeah, I'm declining it because I don't want it to because you're gonna have the recording on a would it be released today though? Today is Friday. It's gonna be a hard ask. When's your exam? I know there's two sections here. So when's the exam for those in Kong's class and when's it for Alla? I think it's different. Let me check the syllabus. Kong is Wednesday. Tomorrow at least we have it on 16th. I can ask to make it release tomorrow. Let me actually text my boss for right now for that to be the case. Um, do we should let me ask one as well. I think there shouldn't be a problem if you one sec. Give me one. iPhone has entered the chat. While I do this, I will check if you all have filled out the form. Backend. Damn it. Next. I hate you, Microsoft. Nope, not doing that one. Mm-mm-mm-mm-mm. Once again, while I'm waiting, feel free to add in specific topics of graphs. So far, we have adjacency matrices, connections, etc. So feel free to add whatever topics you would like. I'm just going to text my boss if you're allowed to um, record on your own device. Connect the graphs, connected, determining how two graphs are isomorphic, what process can we use to find that? Okay, okay. Sounds good. So while my boss responds, okay. Simple graphs. Here's an example of simple graph. So sometimes you can see graphs where different nodes can have multiple edges between them. So here we have LA and Denver have two edges between them. So this is an example of multi-graphs. Sometimes you also have influence graphs. What in the world is an influence graph? If it helps, could you like give me a maybe a practice question? You know, the text could go with that because influence graph sounds very trendy. I'm old. I don't know the trends. But here's an example of graphs with loops, right? So you see once you add like loops and multiple edges, and it doesn't become, I don't think it becomes, I don't think it remains simple anymore. Um, okay, so for those who want to record it on your own device, go for it. If you ask for permission, I will approve it right now. Once the recording is done, my boss said he'll send it to the students, to you students, I mean, to you guys, either today or tomorrow or early tomorrow. Oh, that works too. It will be on the desktop. So, yep, you have permission to take the recording. And my boss did say he will attempt to send out the recording to you guys, the students. The official recording will be posted on the YouTube channel on Monday, but I think he'll send an email with the Zoom recording to either today or early tomorrow. So go for it. If anyone needs to record, I think who's the one who wanted to Alla Sarkar. Sorry if I butchered your name, but if you want to request to record it, go for it, and I'll approve it right now. Okay, approve. Let me know if it's recording on your end. Okay. All right. So now we have an example of graphs. So now once we add these arrows now represent directed graphs, right? So whereas before here, say we had in this graph San Francisco, Denver, right? This with because there's no direction, you could go in either direction, back and forth with the edge. But here, now that it's directed, you can only go in one direction. So I can go from San Francisco to Denver. I can go from Denver to San Francisco, right? And the reason why I'm pointing this out is that later on when we get into matrices and representing graphs with matrices, this will affect like how it represents it. Okay. So right here we got the idea of directed graphs, right? So we got digraph, VE, vertices, edges, Surret, and V instead of directed edges or arcs. Yep. So whenever you have a directed graph, in an undirected graph, UV just means there's an edge between them. But in a directed graph, please note this, the pair UV shows that you start at U and you go to V. So if you want to show it display like this, it looks like this, right? Diagram, right? So this you start at U and I end at V. Okay. And once again, this will also impact how it looks like when matrices. Let's go right here. Okay. If anyone wants to take a quick screenshot of this table, you might, I think you have the textbook too, but if you want to take a screenshot, feel free, and we'll then move on. This is just, we're just briefly going over graphs and everything. Let me know when y'all are ready to move on. And everyone can hear me, right? I'm not too low, not speaking too low. The volume's good. If you need to speak higher, I'll speak higher. Good on your end? All right. Thank you, Raphael. Yes, yes, yes. Let me know when y'all are ready to move on. Just one yes, and I'm moving on. Or we'll move on now. Okay. Okay. Social networks. Yeah, well, these are just going over different uses of graphs, different interpretations. Once again, see, here's example of an acquaintance graph, and here's an influence graph. Oh, so this is what your influence graph is saying. Studies of group behaviors observe that certain people can influence the thinking of others. Very graph. Oh, okay. So this is this the influence graph that I think who's it mentioned? I think Ken. Is this what the influence graph you mentioned looks like? It's basically a directed graph, and it shows that basically, I think it's not mistaken, Brian influences Linda because the arrow points that way. Let me just make sure that's the case. Vertex A can influence a person represented by vertex B. Boom. Yep. There you go. So in a directed graph, in a digraph, if it's an influence graph, we see that the direction is um. So is it like your higher ups in a company type of graph? Yeah, you can think about it like that. Yeah, you can think about maybe Brian is in a higher position than Linda, so he influences what Linda does, and same thing for Deborah and Linda, right? And if I want to say higher ups, it's a bit weird. Maybe you could think about it in terms of like decision making, like L Brian impacts Linda's decision. Like Linda's, if you want to think about it a different way, it's not possible for an influence to have that loops, right? You can't influence yourself. No. Yeah, I wouldn't. I mean, technically, everyone can influence themselves, but I would think you don't include the loop because it's kind of redundant to put that. It's like if you only want to add edges if like outside forces or outside people influence you, so it kind of shows that. So it doesn't really make sense to have loops. You can't. Yeah, even though technically you do influence yourself, it's not really useful to add that in the graph. So that's the influence graph. To be honest, in all my years of teaching this and taking this, I never really noticed this. But does anyone have any questions about that? Right here, see, also we all note this. Because of the double edge here, we see now that Brian and Yvonne, is that Yvonne? They influence each other, right? So whereas this edge right here shows that Brian influences Linda, but Linda does not influence Brian, right? So if you want to think about it in the sense of like higher ups, etc., Brian may be in a higher position than Linda, and that's why whatever Linda does doesn't really impact Brian's decisions, or they might be in separate departments, right? But type of graph is that influencing graph, directed, multi-graph, or it's a directed, I believe. Directed, let's see. Directed multi-graph. Yep, directed multi-graph. So loud. Yeah, so influence graph is a type of directed multi-graph. And we see here Brian and Yvonne influence each other. So they probably have the same level, if that makes sense. Okay, is everyone okay with influence graphs? These are acquaintance graphs, friendship graph. These are more simple. It just shows who's friends with who. Right, so Kamini and Jan are friends. Jan's connected with. Well, in the definition of a directed multigraph, you can have loops, but it's just in influence graphs specifically, it doesn't make sense to have loops, right? This is just saying you can have loops, but like if you have a directed multigraph without loops, it's still a directed multigraph. Yeah, yeah. So that's why it's still an influence graph is still a directed multigraph, but it just you can't have it doesn't make sense to have loops because I mean quite obviously everyone influences themselves and their decisions, so it doesn't really make sense to add that self loop. But this yes, this is an example of a directed multigraph. Any questions? Any questions about that topic? About friendship graphs, or directed multigraphs? No? Okay. So let's keep rolling. Hmm. Collaboration. I really doubt you're going to be asked on specific graphs. These are like this is just applications of the graphs, right? So I wouldn't really worry about whether you're going to be tested on this. These are just once again applications. So I'm gonna unless anyone has any questions about this, I'm gonna like quickly go through. These are just different applications of graphs. Let's scroll through it. Hmm. Okay. Does anyone want to do you all want to do some exercises from this section, or you think you're good and we want to move on to the next one? Next section is graph terminology and Jonathan and where's Jonathan? Jonathan and Oscar. Oscar type one. Wait, Oscar type one? If you haven't filled out the form, fill it out. I think some of you might, but if you haven't, please fill it out. I'm getting a note from Daniel that you might not have filled it out. If you have, then ignore my note. Okay, let's do question one. Okay, so draw a graph model stating a type of graph from table one used to represent airline routes where every day there are four flights from Boston to Newark, two flights from Newark to Boston, three flights from New York to Miami, two flights from Miami to New York, one flight from New York to Detroit, to what the hell? Okay, buddy. Okay, whoa. So let's actually write this out here. Okay, so we know Boston to Newark, there are two flights. And then Newark to Miami, there are, someone catch me if I'm wrong, two flights from New York, four flights from Boston to New York. Emron, it's the attendance form. So I think it's is there multiple forms? Sorry. Thank you, Don, for filling it out. It's just an attendance form. It's the one that Daniel just sent. Damn it, I lost the chat. No, I didn't lose the chat. Never. Okay. Okay, four flights from Boston to New York, two flights from New York to Boston. Keep going. How many am I missing here? Oh God, this is on the wrong page. Five, three flights from New York to Miami. Damn it, I'm losing space. Boston to New York, four. Two from New York to Boston. Three from New York to Miami. Two from Miami to New York. So Miami to New York, there are two. One flight from New York to Detroit. There's one. Two flights from Detroit to New York. There are two. 3 flights from Newark to Washington. 10 Newark's in the middle of everything. 2 flights from Washington to Newark. And 1 flight from Washington to Miami. Okay, I think I got it all. I think I got it all. Okay, so correct me if I'm wrong, someone. Okay. All right, let's draw this out. Blank paper. PDF. Blank document PDF. Fantastic. Okay. So A is asking, no, I don't want edge. An edge between vertices representing cities that have a flight between them in either direction. Okay. So let's do this. So let's draw it out. So we got, this is Boston, put Newark up here. We got Miami, Detroit, Washington. Oh, it ends up working out nice. That's all right. Okay. So one's asking an edge between vertices representing cities that have a flight between them. Okay. So there's a flight between Newark and Boston. There exists a flight between Newark and Miami. Yes. As long as you get like the edges between the vertices correct, and it doesn't really matter where you draw each vertex or the I mean which orientation, as long as the edges are good. Like as long as this edge BN exists, then that's fine. Newark to Detroit, Newark to Washington, and Washington to Miami. Okay. So this is an example of a yes, duplicate tab, page are we on 705. This is an example of a, I went too far back, of a simple graph, right? So undirected edges, multiple edges are not allowed, and no loops. So right here is an example of a simple graph. Okay, so a few more. An edge between vertices representing cities for each flight that operates between them in either direction. Okay, so now it changes up a bit. Well, actually, pretty much. Because now we have, this is New York. I'll draw it a bit smaller. Right? So now here, this is a bit different because now we have an edge between each vertex representing the cities for each flight that operates between them. Okay, so now we have one edge per flight. Let me bring this down. There you go. Okay, so how many flights are between Boston and Newark in total? Someone answer. User um in thing. Is it just 4? Remember, we're just saying all the flights, doesn't matter where it's start or end. Yep, we'll go over those in a bit. 6, right? So we're gonna draw 6. So that's 1, 2, 3, 4, 5, 6. Okay. Do you see how that's the case again? That's because you have 4 from Boston to New York and 2 from New York to Boston. So you have to add them together. All right. So now what about from Newark to Miami? Mm-hmm. 1, 2, 3, Um, New York to Detroit. Mm-hmm. Agree. Washington. New York to Washington. Bingo. It's not gonna look pretty, but it's gonna look really weird. It looks like a weird person. And Washington to Miami is just one. Okay. This is an example of a multigraph. They have multiple edges between each node, each vertex. Questions? Any questions so far? Let's see what the next one is. Okay. So now the next one is actually pretty simple because now it's the same thing as B, where it's an edge between vertices representing cities for each flight that operates between them in either direction, plus a loop for a special sightseeing trip that takes off and lands in Miami. Now we have the same graph, but with a self loop. Self loop, right? So here's an example of a pseudograph. Because undirected, we have multiple edges, but now we have a loop. So this is a pseudograph. Okay. I might be going through this a bit quickly, but we're just gonna try and get as much graph stuff in as we can. So now an edge from a vertex representing a city where a flight starts to the vertex representing the city where the flight ends. An edge from a vertex representing a city where the flight starts. Okay. So now here, let's go back to the first graph because now we're going to edit it. Because now we have an edge from a vertex representing a city where a flight starts to the vertex representing the city where it ends. So now what does it mean? We're just going to change this by doing this. We have a flight from Boston to New York, and we also have flights that go from Newark to Boston. Same thing for here. We have one that goes from Detroit to New York, and we have flights that go from Newark to Detroit. Right? Same thing for New York to Washington and Washington to New York. We have a flight that goes from New York to Miami and Miami back to New York. And we have one that goes from Washington to Miami and only there. We can't go back because the only flight that goes from Washington to Miami. There's no flights from Miami to Washington, right? So we see here how this is an example of a simple directed multigraph. Yep, I think this is right. Because now we have an edge that goes, this edge represents these flights, this edge. Um, this edge represents these flights, and we keep going. Because we have an edge that goes from the starting position to ending position, if there exists a flight, right? And the last one, I'm not going to really draw it out because it's pretty similar to the one we just did, in that an edge for each flight from a vertex representing a city where the flight begins, the vertex representing the city where the flight ends. So basically you're adding arrows to all of these edges, except the loop, unless the loop's part of it. Right, so you would add arrows. For example, let's do Boston to New York. There's 4 flights from Boston to New York. 1, 2, 3, 4. And there's 2 flights from New York to Boston. Okay. So what keyword tells us it's a directed multigraph to a direct simple graph? I think the idea is simple directed graphs. The main thing you should look out for is if there's no multiple edges and no loops. Once you see a loop, then you know it's a directed multigraph. For like, if anything, look at the multiple edges as well. Because you can't, simple graphs can't have multiple edges between them, right? Because then it's no longer simple. There's different routes you could take. If it's a single edge, then where it was how this example was in the beginning, then that's just a simple directed graph, right? So if I took out these um extra loops, then it would become a simple directed graph, right? Once we add multiple edges, then it becomes um multigraph because there's multiple edges to think of. Make sense? Everyone okay with that notion? Any questions so far? To the next topic. What are the theorems that your professor uses? Okay. Mm-mm-mm. Or the handshake theorem, congruent over. Yeah. Handshake theorem. Okay, let's do. Should we go over these definitions? Hopefully, I'm assuming you guys know these definitions. So we know in an undirected graph, stop typing. Two vertices U and V, undirected graph, they're adjacent, right? So this is basically introducing terminology. You'll see this a lot more in like 323 or 313 or another graph or CS related subjects where you'll talk a lot more about um, graphs and graph theory. But here is the idea of adjacency, and this will lead to the adjacency matrix and etc. But we only call two vertices adjacent if they share an edge, right? So in a graph, this is U, all matching theorem. Anyway, yep. Okay, sounds good. This is U. This is V. So we know that U and V are adjacent because they share an edge. Let's call this edge E. Okay. And now comes the notion of a neighborhood. If there exists a subgraph, let's talk a bit more about a subgraph or a subset, right? So if I can create some subset of V denoted by N of A, where that are adjacent vertices. Okay, the set of all neighbors of vertex V. Okay, neighborhood of V. Okay, so this is basically if I had then have, let's say I add another W, another one Z, right? And I have edges from here to here and here to here. Basically, if I take the graph and I take some random vertex, say U, and I find every vertex that is connected to U, right? These vertices then become the neighborhood of U. In this case, I use V, but it's the same topic. These are, think of it as basically all the nodes or vertices that share an edge with some, we choose a vertex and they all share an edge with that vertex. Okay, is everyone okay with that notion? And lastly, when it comes to degree, I think degree is what you'll be using in the handshaking theorem. Basically, it's like an underdirected graph is the number of edges incident with it. So basically, the number of edges that come out of the specific node. So for example, here, the degree of U is going to be 3. Can you explain example one more thoroughly on the same page? Okay, let's do that real quick then. What are the degrees and what are the neighborhoods of the vertices in the graphs G and H displayed in figure 1? Okay, let's do a couple examples. Let's take this graph here. Okay. So let's look at A. So what is the degree of A? How many edges connect A with other vertices? 2. Mhm. So the degree of A is 2. And what is the neighborhood going to be? So the neighborhood of A. What nodes, you could see the letters, share a connection with A? Yep. Right here, Amron, you can see for a neighborhood, yeah, you got to specify which ones. So it's B and F. Okay, let's do two more from this example. How about C? What is the degree of C? It's not three. Yep, it's four. All right, we got one edge, two edge, three edge, and four edges. So there's four edges that come out of it and connect it to different nodes. Yep, no worries. You gotta be sure to count them, right? And based off that, what is the neighborhood going to be of C? B, D, F, E. Yep. I just realized I can type them down. Okay, anyways. All right, let's do one more. Let's do a little G right here. What's going to be the degree of G? Yep, zero, right? Because there's no edges connecting G with any other um, node. And what is going to be the neighborhood of C? I'm sorry, neighborhood of G then? No, or the empty set, right? Nothing. Because there's no edge, sorry, no vertex that's connected with G. Okay. Also, I will note about a degree, when it comes to loops within an undirected graph, they count twice. Why? Because think of it as like, if you expand the loop, it's like an edge from B to B, right? So in here, B is plus one, B is plus one, and you add them, it's going to be plus two. Okay, so loops count twice. Loops add plus two. A, that'll be two. So when we go to major C, the loop will like be A. Right here? Are you talking about this A or this A? Are you talking about B? B in this example. Um, Matrices, if it's a degree, I don't think it's a degree, but if you were to put the degrees of each matrix in the matrix, yeah, you would then add two. So whatever the value of B is without the loop, you would add two to that. So for example, let's jump here right now. What's going to be the degree of B? I can't, not drawing anymore. What's the degree of B? Yep, six. Yep, it's six because now you have one for A, B to E, B to D, B to C. That's four. And now we have a self loop, but that's two. Because remember, self loop you expand it, it's B to B. You add once for each time you see B, and that's plus two. So it's six. And now here, what's going to be the neighborhood of B? What nodes are connected to B? Okay, we got A, D, E, C. Anything else? B. Mm-hmm. B itself, because there's a self loop. Okay. Yeah, you don't repeat B because it's a, even though it's a self loop and you expand it to B B, you don't really need to add it twice because it's already there. Okay. You want to do also one more example from here? So let's pick E. I will show where the recording will be uploaded at the end, but for now it'll be on the Learning Commons website. I'll show it at the end after we finish most of the review. But It will be there. And I think for those of you who are in comp class, or I think just everyone here, you'll get an email of the recording, the Zoom recording, either later today or early tomorrow. So the degree of E is 6. Yep. The degree of E is 6. Right? Because you got two edges from E to A, three from E to D, and one from E to B. So now what's going to be the neighborhood of E though? Because remember, you do not, you're going to set, you do not repeat. So we got A, B, D. Okay. Only three notes. Everyone okay with that notion? You don't you just because there's two edges from E to A doesn't mean you add E twice. It's already there, so you just leave it. There's a typo. That's not, I'm sorry. A. Thank you. Just because there's two edges from E to A doesn't mean you add A twice. You just add it once. Because in a set, you don't repeat stuff. Okay? Any questions so far? So far, so good. Right? Sounds good. Okay, let's keep going. Mm, mm, mm. Okay, handshaking theorem. So if you want to think about it intuitively, um, okay, we have a graph with vertices and edges, an undirected graph with m edges. Then this is basically saying if I take 2 times the number of edges, right, then that will equal the total, if you add up the degree of every vertex in G, that would equal 2 times the number of edges. Does anyone have an idea why this intuitively makes sense? Think handshaking. How many people do you need to do a handshake? Well, to a regular handshake. Daniel, you cannot be answering the questions. You already took this class. Mm-hmm. Right? So that's the whole reason behind the handshaking theorem. If I have two vertices in a graph, one edge, right? So this edge is in one of the M edges. This is one. It always connects to two vertices, right? You can't have an edge that only like juts out of one vertex. And you can't have one edge that kind of like connects all three, right? Then this just becomes two edges, right? So one edge always connects two vertices. This is always the case. Okay. And then what this means is that this edge will then count +1 to this vertex and +1 to this vertex. Both are the degrees. And this edge will count +1 to the respective degrees, right? So even if there's other edges here, same thing here, this edge will count to the total degrees. It'll count 2 times because it's connected to two vertices. And thus, that's why if we take the total number of edges, and this works even if there's multiple edges or loops, because every edge needs to connect two graphs. And remember, this is also a key reason why back here, the degree of a loop is 2. You add +2. Contributes twice. And thus, so if I take the total number of edges and multiply by 2, that is going to be equal to the sum of all the degrees in G. Is everyone okay with that notion? Everyone okay? So a quick example right here they give. How many edges are there in a graph with 10 vertices, each of degree 6? Well, okay. If there's 10 vertices, each of degree 6, that means if I add up their degrees, the inches below, let's ignore for now. If I were to add up all the degrees, this is going to be 6 plus dot 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 plus 6, it's just 10 times, which is just 6 times 10, that's 60. And we know that is equal to 2 times the number of edges. Divide both sides by 2. I get that there are 30 edges. Okay? Any questions about that? I'll wait a minute while everyone catches up. Is everyone okay with this notion, the handshaking theorem? It's not too bad once you like think about it intuitively. And work feels good. Is everyone else good? I'll take the silence as no questions. All right, this is another quick theorem. An undirected graph that has an even number of vertices has an even number of vertices of odd edge. Okay. This is also, you could see it here, right? It's just technically the proof for it. But if once again you want to think about it intuitively, just think about it like this. Because remember, from the handshaking theorem, every edge needs to have two vertices. Right? So say I have vertex U and V. U and U and V. Right? So V is of odd degree. Right? So let's say this is 3. Right? Well, these three have to connect to edges, not to edges, to vertices. Right? 1, 2, 3. Right? So say this is our graph. This is W, Z. They have to um they have to sorry, I'm blanking. I lost my train of thought. Where was I? Okay. They have to all be there has to be even number of odd degree. Okay. So what we see here, the degree of V is 3, the degree of W is 1, 1, 1. So there is an even number. There's 4 vertices here that have an odd degree. Once again, why is this the case? Because firstly, every edge needs to connect two vertices. So say I then create this vertex right here, W becomes even, right? But then I introduce a new vertex, let's say this is X. Now that's odd, right? So then you can intuitively like expand this, maybe with induction, and show that you'll always have an even number of odd degree vertices, right? Because every edge has to share between two vertices. Another way of proving this is that if you see here from our last theorem, the sum of all degrees is always even. 2m is always an even number. So the sum has to always be even. And if that's the case, if I have an odd number of vertices of odd degree, then the sum will be odd. Well, that's a contradiction because we know from the handshaking theorem that the sum of all degrees in a graph has to be even. Or more specifically, 2 times the number of edges, which is always even. Okay, is everyone okay with that? Any questions about this? Well, this definition, then we'll go into like these next definitions, and then we'll just speed run the next. Just quickly go over this. So now we'll go into the directed edges cases. When it comes to directed edges, you have now it changes the definition of adjacency a bit, in that we say that U is adjacent to V. Um, Adjacent from U. Um, okay. Right. So here it's the same. It's a similar notion as in the last previous, where like basically UV means there's a connection between U and V. But when it comes to directed edges, remember directed edges means if you have this, this line can go in both directions. But once I assign arrows to it and direct it, I can't like go in one direction and come back. No. So this coordinate UV means that they're U is adjacent to V and V is adjacent from U. This basically means I can go from U to V. There's a directed edge from U pointing towards V. Okay, U is called the initial vertex, V is called the terminal. Right. So for example, for in a graph, if I'm able to, if I want to make it so that I am, let me I'll get to your question in a bit. Um, if I want it to be the case, I can go from U to V in either direction. There, in a directed graph, UV needs to exist and VU needs to exist. Okay, so both need to exist for me to go back and forth. Okay. Question Ramil put. Types of proof questions you might expect to see related to this section. Typically prove the handshaking theorem, prove theorem 2, or prove something using handshaking theorem. It'll be most likely either prove something using the handshaking theorem, so maybe something like this, or maybe it's a case of proving the handshaking theorem itself. From this section, I don't really think you'll get anything out of those two. Maybe something like this, where let's go over directed edges real quick. The in degree, this is basically number of edges via the terminal. The out degree. Okay, so let's use this example real quick to show it. The in degree of a vertex is basically the number of edges that point towards it. So we got 1 and we got 2. So the in degree of B is going to be 2. The out degree is basically the number of edges that point away from a vertex. So the out degree of B is going to be 1. Okay. Here, when it comes to loops, this one's a bit simpler because now you have what's it called? The direction. So now instead of just adding 2 to the degree, it contributes 1 to the in degree and 1 to the out degree. Because if you think about it, a loop means I can go from A to A and A back to A. Right? So this is A, this is A. Okay, so using that terminology, what would be the in degree of D? 2. Right? We got 1, we got 2. What would be the out degree of D? 2. You got 1, you got 2. All right, what would be the in degree of A? 2. This edge goes in once, and right here. What would be the out degree? 4, right? So this edge once again counts out. 2, 3, 4. Any questions? Back to your question of what's it called? Proofs. Once again, you would most likely gonna get something of this type where it's like prove an even number of vertices of odd degree, or maybe proving the handshaking theorem. You won't see as much proof when it comes to this section of graphs. But yeah, and one more thing here. This is basically pretty simple. If I have a graph with edges, vertices and edges, direct edges, then the in degree of every vertex plus the out degree is equal to the total number of edges. This is pretty much obvious because if I were to add all the in degrees of each vertex and the out degrees of each vertex, I would get every single degree, and that's the total number of edges. Okay? So those are like most likely the proofs you're gonna get. All right, let's keep going. All right. Special types of single graphs. So we got complete graphs. Complete graphs are where every vertex is connected to every other vertex. Okay. So here's an example. Here you have K1 is just one node, vertex. K2, here we have the two nodes are connected to each other. K3, everything is connected to everything else. K4, K5, K6, right? And then they're related to cycles. A cycle is if I were to have, so n has to be greater than or equal to 3, right? Because this technically these aren't, they are cycles, but you can ignore them. But if we had, they're basically, if you want to think about it, if you put only the edges exist on the outer, right? So you just connect every edge outward. You don't have any inward edges. So it's basically a complete graph without the inner edges. Okay. However, you could take a cycle, and if you add an extra vertex in the middle, right? And every outer vertex then connects to that inner vertex, that becomes a wheel, right? So these are examples of wheels, and you'll see how we obtain these wheels from cycles. Okay. Hypercubes, I don't really think you gotta know this, or need to know this, but you still need to know. Here we have three examples. It's basically everything is connected to everything else, but now it's taking into multiple dimensions. Q4 doesn't exist because haven't cracked the fourth dimension yet. But yeah, that's hypercubes. You won't really need to know that, but all right, bipartite graphs. Before I go on, are there any questions? Am I going too fast? Everyone okay? What do you mean by switching bits? Think of like listing out each, giving goes to 0, 0. Yeah, I mean you can think about it like that. Yeah, it's basically like binary numbers. I said 0, 1, 2. I think this is 3, and then 4, 5, 6, 7. So it's 0 to 7. I mean, I wouldn't, because you can only represent the three of them because you can't really draw the fourth one. But like, if you still want to remember it, yeah, you could. Should know things like the number formula to calculate numbers of edges for types of simple graphs. Relations to that. Yes, I would say yes, especially like the handshaking theorem that could be useful, right? When it comes to like exam questions, I would say specifically go off of homework questions, whatever homework questions he gives. That'll be like your best bet. Whatever he goes over in class, but specifically the homework questions. So that would be, yeah, it is useful. If you're in Kong's class, I'm pretty sure you get a one-page cheat sheet. So you feel free to put those formulas on that cheat sheet. Any other questions before we go over bipartite graphs? A few minutes. Give my voice a tiny break. Okay. Bipartite graphs. Sorry, it's just I've been speaking for like the past hour and I had another meeting for this and I had class in the morning. I'm just tired. I do not want to be awake anymore. Gonna sleep. Okay, bipartite graphs. Okay, the idea of bipartite graphs is if we can take a graph and basically split it such that we end up with two sets of vertices where everything from one set goes to only the other set and vice versa, right? If you want to think about it like this, we can take vertex set V and partition it into two disjoint vertex sets V1 and V2, such that every edge in the graph connects a vertex in V1 and a vertex in V2. So everything from V1 only goes from V1 to V2. No vertices in V1 connect with each other, right? So this then becomes a bipartition of the vertex set V of G. Okay. So, and this is a nice visualization to show that it is the case, right? So we see here V1, everything in V1 goes only to V2, right? Nothing in V1 connects within each other. It's only from one to another. Okay. And a nice trick that I learned that this is what you'll eventually learn in 323 in order to learn if graphs are bipartite. It's a nice coloring trick. Okay. So what do? We go through each node in the graph and we color it. And the idea is if a node is a and we can only use two colors, right? So let's use this, write this out. Coloring technique. Only two colors and no two nodes with a shared edge can be the same color. Okay. So and the idea is if we can do it with only two colors, boom, the graph's bipartite. If we can't, then it's not bipartite. Okay, so let's use two colors. Let's start with this graph. So A, we're going to make it green. Boom. G. G is connected with A, so it can't be green. Let's make it red. Okay. What color can F be? Green or red? Red. Hmm? Because it's connected to A, which is green. So it can't be green, but it's not connected with anything that's red. All right, E. What color can E be? Red. Right? Because it's connected with A, which is green. So it has the only option left is red, and it's not connected with anything that's red. All right, what about D? What color can D be? Green. hmm Because the only vertices that are colored connected to D are red ones. So G, F, E are all red. D shares it with the three of them, so it has to be the other color. Okay, C. What color should C be? Red. Okay. C is red. A is green. Green looks good. And lastly, what color can B be? Green. And it works out, right? Because everything connected with B is red, and thus B can only be green. And B is not connected with anything that's green. Okay? So now we know that G is bipartite. Any questions? See, this is why I like this. T's are like, I mean, I think this strategy might be your best bet, but when it comes to like 30 vertices, not 30, 40 vertices, I see what you mean. It could be like a bit very tedious. Um, but I think this might be the best bet, especially like, yeah, it is tedious and time consuming, but I don't, unless it's like pretty obvious. It's hard to like specifically see. So the colors do help. Oh yeah, that's true. So like in graphs where it is like very large, something you could do to prove that it is like if it is glaringly obvious, if you see that if there are triangles, like you mentioned, then boom, like right here. Let's example here. Let's start with coloring. F is going to be red. Let's do red, orange. By that logic, A can only be different colors. So let's pick blue. And if you look at B, right? I think the best strategy is like a number 15-second rule to spot out odd amount of edges from one vertex to another. Well, that's another one. Yeah, we see here that any vertex with an odd degree, right? So all these vertices. I mean, this to be fair, B has an odd degree. C has an odd degree. D has even. No, F is odd. Oh, okay, I see. So me personally, I liked the coloring technique. Another strategy you could use is like Ramil mentioned is the triangle. So here is a triangle, right? B is connected with A, which is blue, so B can't be blue, but it's also connected to F, which is orange, so B can't be orange. And those are only two options, so this is not bipartite. I'm not sure about the 15-second rule to spot out odd amount of edges from one vertex to another. If that works for you and you think it's a nice strategy, go for it. I haven't done it enough to like know. But smaller strategies, 15 seconds to answer a question. Sheesh. Okay, anyways. That is another technique. Damn, 15 seconds to answer a question is insane. I don't know how many questions he's gonna put, but the triangle is a neat technique. Like if you see a triangle, boom, it's not gonna be bipartite right off the bat because it's you have all three connected to each other and you can't really another one example is this is B, let's say B is one color, E is a different color, D can't be either one of those colors. So it's automatically boom, no longer bipartite. Okay. So so yeah, here's the theorem, right? And you will see later on when you do like later CS classes, like I think 323 or other um algorithmic type classes, where you'll use the coloring algorithm in order to see if you have bipartite graphs. So especially when coding, this one's pretty neat. And it's not that bad to implement either. So any questions about bipartite graphs? No questions? A special type of bipartite graph can be complete bipartite graphs. So if we go up here, C6, C6 is a complete graph, and we see here specifically that, oh, I'm sorry, never mind. Complete bipartite graph, right here. Okay, here is a complete bipartite graph. I'm sorry. Complete bipartite graphs are bipartite, where we can split them up into two sets, such that no two edges within this one set are connected with each other, but they're all connected with everything else. But the idea is with complete is that these two are connected with all three of the vertices in the other set, right? Same thing with these three. So this is the other examples of complete bipartite graphs, right? If say, for example, this edge didn't exist, it would still be bipartite, but it's not going to be complete. Same thing here. So we have complete 3, 5, where there's three nodes in one set, 5 nodes in the other set, and every one of the three nodes here are connected with all 5 of the nodes in the other set. Same thing for the 5 nodes here, connected with the 3 nodes here. So all the nodes, and say this is set X. I'll use X. Let's use V1, V2, right? So all the nodes in set V2, V1 have degree 5, and all the nodes in set V2 have degree 3 because they're connected with the 3 here. V1 is connected with 5 here. Okay. So any questions about complete bipartite graph? I think, yeah. Here's some uses of bipartite graphs. So you can do job assignments, right? You can't have, so here's an example of job assignments. Oh, the marriage theorem, Hall's marriage theorem. Before I go into here, does anyone have any questions about complete bipartite graphs? Any questions? I'll wait a minute. Sounds good. More so about matching. Okay, let's do some matching. Matchings. Okay. Okay. Sorry. So when it comes to matchings, the idea of a matching is that, let's think about it in terms of jobs. Let's do an example of jobs. A matching, and this will end up being a big thing when you learn in 2023, the stable matching problem and the stable marriage problem. But the idea of a matching is that it's bipartite, but no one edge, no one node can be matched with more than one, right? So for example, if you think about it in terms of jobs, we can't match one person with multiple jobs, right? You only have one job. Here it's different where it's like trained, where you can go to one person can be trained in different fields. But here, if I were to match someone to jobs, I can't match Alvarez to requirements in architecture. Because if that's the case, then it could be one of the other ones doesn't get a job. And multiple people doing the same job doesn't really make sense. And that leads us to this question: marriages in Hall's marriage theorem, where we're given a bipartite graph, G with vertices and edges, has a bipartition if and only if the neighborhood of A is greater than or equal to A for all subsets A of V. Oh, it's a long one. Basically, it's just saying if I have any any vertex A, and complete matching, it's complete match only if neighborhood of A is equal to A. Sorry about that. Just look at the proof real quick. Hmm. I don't think we have to prove this. This is a long proof. Let me think of an intuitive way to explain this. Our partition V1, V2 has complete matching for V1, V2 if and bipartite neighborhood. Okay. So let me actually think about it like this. If I had, because this is saying if it's a complete matching, let's say I have one, two, three, one, two, three. So we got one, two, three, one, two, three, one, two, three. Okay, so that means if A is this, neighborhood of A is three, three, three. Oh, I see it. Okay. A becomes A becomes this. Yep, okay. So I don't think you're gonna be asked to prove this because this is like use one where it's like the proof. But if you want to look at it intuitively, let's think about it like this. We know that there's a complete matching if regardless whatever subset of so if we go back, we remember the idea of neighborhoods of vertices. We could also do a neighborhood of a set of vertices, right? And that's basically all the vertices that are connected to one of the vertices in that set. So for example, if A is a set of vertices, let's say this is V1, V2, etc. In the neighborhood of A is going to be the set of all vertices that each vertex is connected with at least one in A, one vertex in A. So now this is saying that regardless of whatever subset of vertices I take from the bipartite graph, um, I will get a complete matching if and only if the neighborhood of whatever subset I take is greater than the number of vertices in that set. You're gonna have to like if you need to prove it, you need to prove it with induction. I'm not sure if Kong teaches induction. He does a lot of graph stuff, but so I think that's why he won't ask this proof. But intuitively, if you look at it like visually, you see that's the case because if I were to choose one, right, one vertex in one of the sets, well, by definition of bipartite, it has to have at least one connection with another vertex in the other set, right? So this being the case, if I take, for example, this is of size three, this set, right? And if I take all three, well, all three, if it's complete, they have to have at least three. The neighborhood of this has to be at least three, or the size. It can't be less than three. Because if it's less than three, then it's the case that one of these isn't connected to one of the other ones. And this it's not complete. Is everyone okay with this? I'm kind of butchering the proof. I'm trying to like explain it intuitively. I'm not sure if it's working. Um, is everyone okay with that? Sort of. Hopefully. Um, example. And when you think about an example, like it's better to like draw things out. So for example, here's an example of a complete K33, K33. Let's actually use one of them here, right? So for example, let's do this K26. If I were to take this is my set A, or exercise, okay, let's just do this one example real quick. Then the neighborhood of A would be 6, right? If I take the neighborhood of these two, it's going to be 1, 2, 3, 4, 5, 6 still. 6 is greater than 2. Now if I expand it to these four, these two have 6, these two have 2, so the neighborhood of this is going to be 8, right? So see how the neighborhood of these four is always going to be greater than or equal to the number of vertices inside of it? So that's kind of the proof behind it. And because this is the case, regardless of however big I take it, so if I were to take even all eight of them, well, what's the neighborhood of all eight? Well, it's just eight. So eight, is it true that eight's greater than or equal to eight? Yeah. So that's how I think it intuitively you can see it. Let's move on to exercises, and then maybe that'll help out. Special graphs, interconnection. If you're gonna leave, please do fill out the feedback form. Let me know if I'm skipping over something that someone wants to go over. Exercises. What was it? 26 to 30. Okay. Okay. So which one do y'all want? 27 to 30. Okay. Suppose there are four employees in the computer support program, the School of Engineering in a large university. Each employee will be assigned to support one of four different areas: hardware, software, networking, and wireless. Suppose that Ping is qualified to support hardware, networking, and wireless. Quigley is qualified to support software and networking. Ruiz is qualified to support networking and wireless. And Satia is qualified to support hardware. Uh, One sec. Wow, that really messed up the thing. Damn, I really hate this. Come on. Okay, that was a doozy. Suppose that there are four employees in the computer support group of the yada yada yada. Okay, so let's write this out. It's annoying that they use the same name. Okay, Ping is gonna be here. Quigley, Quigley, Ruiz, Satia. Damn it. Okay, and we have hardware, software, networking, and wireless. Okay. All right, use a bipartite graph to model the four employees and their qualifications. So what do we know? We know that Ping is qualified for software and hardware and networking and wireless. Very good. Um, please make sure I'm not making mistakes. Mm-mm-mm. Quickly, software and networking. We just qualified to support networking and wireless. Support hardware. Well, it's and software. Bingo. Okay. Let's go back and make sure. Okay. Oh, complete matching. Wait a minute. Wait a minute. Wait a minute. Oh, I'm sorry. A complete matching means that everyone in this side can be matched to at least one thing from here. So like think about it like this. If it was like you'll see this problem in 323 a lot, the stable marriage problem. If I can match every person in one set, like think of this in stable marriage problem, you'll see as like instead of men and women, if every man can get matched to a woman, then there'll be that counts as a matching, complete stable matching, right? So I think I might have made a mistake before. Whoa, everyone's back. Um, but the idea is here is that we want to prove that we can match every person to at least one job. Okay, perfect. Complete matching the same. Complete matching. Complete matching is that. mm, I want to confuse you with 323 stuff. Before I go on, do you guys know what the stable marriage problem is? Did Kong or Alla bring it up? I don't want to confuse you. That's why I'm trying to like not go too far ahead. Okay, if you brought it up, I don't want because the thing is, I don't want to confuse you. The idea of a perfect matching is think about it like this. Um, Stable marriage, yeah. Did he bring that up? Do you guys know or at least heard of that notion? It's a very, very like historical problem. Hmm. Okay. I don't want to confuse you, but like to briefly go into it, think about it like this. Imagine each person here. They like not only they like match to whoever they match with, but they listed how good, like how much they want to in a sense. For example, if if it's the case that all four can do all four, right? And see here's gonna be Ping. Ping's gonna rate which of the four he or she wants in like preference, right? Same thing for Quigley, same thing for Ruiz, and same thing for Sutia, right? They're gonna have preferences. And they're gonna be listing out I want to do Ping can be like I want to do hardware first, then network, then software, then wireless, right? For everyone. The idea is then first you need to see if there's a matching possible, right? So that comes to the idea of complete matching. Can I firstly match every person to a role or job, right? If it's then that's the case, then we could then it comes the idea of like a perfect matching. Is everyone matched to like their highest choice such that no one can like complain in a sense? Is everyone okay with that notion? I don't want to go too far into like 323 material, but that's kind of the difference between the complete and like matching. Maximum matching. The idea of maximum matching is that like here, if the maximum matching is equal to for what you just described. Oh, okay. But the idea of a maximum matching is that if the maximum matching is equal to say the set, um, so say this is V1 and V2, and say M is our maximum matching. If maximum matching is equal to the size of V1, which is hopefully equal to the size of V2, right? Then this is a complete matching, right? If it's the case that V1 isn't equal to V2, then the maximum matching is always going to be the minimum of the both, right? So if V1 is not equal to V2, then the maximum matching is going to be equal to, at max, the minimum, but this is going to be less than or equal to the minimum of V1, V2. Okay? Because as an example, if we look here, go back up to the complete graphs, an example. I can't match three people with two people because you can't match, well, intuitively, you can't match two people to the same person. So in here, the maximum matching can only be two because that's the size of the smallest set, right? So then it comes to your example here, right? Um, Here's a similar example, or we have it here. I think Kin mentioned every person has at least one role, thus Hall's theorem validates notion, right? So I can technically match. If you want to do like Hall's theorems fully, you basically take a subset. So what's the um, neighborhood of P? Well, it's four vertices, which is greater than one, so that's good. Neighborhood of Q is going to be also four, greater than two. Neighborhood of R is four, which is greater than or equal to three. S is four, which is also greater than or equal to three. Same thing for W. W is going to be six, which is greater than or equal to five. N, like, am I going too fast? Is everyone? Basically, you go through each node and you find the size of their neighborhoods, basically the size of the set for each neighborhood. And then if that's greater than or equal to the number of vertices in the set that you're looking for, then the Hall's theorem holds. So it's possible to have a complete matching. One example of that is say I do ping gets hardware. Da, da, da. Why did I do these three in different colors? I have no idea. Um, let's say, let's think about it like this. Do, do, do. Satya can get hardware. If Satya gets hardware, that means Ruiz can get networking. Um, Quigley can get software, and Ping can get wireless. Right? So now we see there exists a complete matching. Every person gets one role in the matching. Okay? If I were to then introduce, like, say, preferences, like, say, maybe it's the case that Ping prefers um, hardware more than wireless, right? And say if it's the case that Satya prefers software more than hardware, then that wouldn't be stable. But I don't want to confuse you, so ignore what I just said. But that you'll see later on, like the idea of stable matches when you get to 323. And here, maximum matching, the value of the maximum matching is going to be 4 because we've managed to match everyone to all four of the nodes in each set. Okay. Does anyone have any questions? I've spoken a lot, and I don't want to make sure I don't lose any of you. So I want to hold a quick minute break to see if anyone has any questions. Any questions at all? I don't know whether the silence is good or bad. I'm not entirely sure. Okay. Okay. Do we want to? Okay, this and yep, this is part C as well. So boom, boom, boom. 27 done. Let's try to see. Look at. Let's do one more example of Paul's questions, and we'll quickly do adjacency matrices before I forget. Isomorphism. We'll do that right now. If anyone, do you want to do at least one of? Do you want to do one more questions of these? Because I think most of them are the same thing. Um, do we want to do one more, or do you want to go over to matrices and isomorphism? Let's go over isomorphism then. Okay. Sorry, guys, it's been a long day for me. Okay, so when it comes to representing graphs, you have to remember computers, we can't like give them pictures. We have to like find a way to, well, programming, we have to find a way to represent these graphs in various ways such that we could like do operations with them. So it comes to different ways we could represent them. So here's an example of an adjacency list. Basically, you take every vertex and you have a list of any vertex that is adjacent to that vertex. So for example, here would be A is adjacent to B, C, and E, right? B is adjacent to A, and for everything else, right? So how would you implement this in code? Basically, for each node in the graph, you would store like a list of adjacent vertices. Okay, same thing here. For a directed graph, an example is a similar notion, but you would do it with for every initial vertex, you would add the terminal vertices. So the initial vertex every edge from A goes from A to these nodes. Okay. Same thing for B, C, and D. And when you see loops, right? These basically mean that like B can go to B, right? Very simple. Matrices are like this. It's all ones, and we have it of this case. Say this is going to be A, B, C, D. If any of you here are like sports fans, think about it like each team facing each other team, right? So if there's an edge from one vertex to a different vertex, we put a 1. Otherwise, we put a 0. And here, because we're assuming no loops, we put zeros for in the diagonal, right? So there's an edge between A to B, so there's a 1. And because it's undirected, that means A to B, the same thing as B to A. And thus, the edge from B to A is also 1. A to B is 1, B to A is 1. Same thing from A to C, A to D, etc. Okay? And you could take these graphs, you could take these matrices and create graphs. Okay? So here we have, once again, A, B, C, D, and we have A, B, C, D. Okay? Give me 1 second, everyone. And I'm back. Sorry. So we see here. So we have a 1 from A to B. So same thing here. And I want you to also notice that these graphs are, I'm not sure if anyone here is taking linear algebra, but if you have, you'll see that these are symmetric over the diagonal, right? So basically, because it's there's no direction, it's a simple graph. If I have an edge from A to B, that implies I have an edge from B to A, right? So same thing here. So A to B, B to A is 1. So that it goes back to our handshaking theorem. Same thing from A to C, right here. And then we have from B to D and D to B. And then D to C is right here. Okay. Any questions so far? It doesn't, I'm not gonna say it's gonna get complicated, but basically once you have like a pseudograph where it's like you have multiple edges, now that basically means you just have more than one. It could be more than one, right? So what's texting me? If I wanted to label all the edges from A to B, there's 3 of them. So I just put, was it A, B, C, D, B, C, D. That means A to B is 3. And same thing, because it's no direction, B to A is also similarly. Okay. And loops in here, because it's a pseudograph loops. If there are loops, basically that means C to C is 1. Right? I can go from 1 to C to C and 1 from C to C. If it's not 2, because remember this counts twice. It's like if I were to take this and like extrapolate it to one line and both sides are C. So from C to C is 1 and from C to C is 1. So this is only 1. But when you count the degrees, it would count twice. Okay? And these are an example of pseudographs. Is there any questions so far before I keep going? I'm just motoring along. Um, any questions? Oh, okay. Another version of a ma incidence matrix. Can I go over the BB thing? This one, the loop. Okay. So the idea of remember how before when earlier in the review session we went over that if there's a loop in a graph that it counts towards +2 to the degree of a vertex. Well, here if you have the adjacency matrix, remember for simple graphs loops don't exist, so it's zeros in the diagonal. But in pseudographs loops can exist. So whenever there's a loop, right? We add that once per loop. So here's one loop. So that would be it would be 1. Why 1? Because remember, if I were to extrapolate this loop to one line, I'll get one edge from C to C. And remember, sports people, this is home team, away team. So from C to C is 1. And then from C to C is also 1. That's why in the degree it would count twice, but in the matrix you would only add it once. It's only 1. It make sense? Is everyone okay with that? Does that make sense? The notion? Any questions? Any questions so far? No problem. Trade-offs. Basically, what I would say is if there's only one, like if it's only possible to have one edge between nodes, always use an adjacency matrix. Um, Personally prefer when it comes to like graphs, you'll see later on, I think maybe after this first exam, when it comes to you'll do operations with adjacency matrices to like find like roots, number of roots. So in that situation, adjacency matrices are useful. But when it comes to like say programming lists, the lists adjacency lists can be a bit more useful in like seeing which one's connected to which. But both have their use cases, so it's neat to have both in your back pocket and knowing how to do both. Okay. Okay, incidence matrices. Incidence matrices. What were the other topics you want to go over? Isomorphism. Okay. So incidence matrices. Incidence matrices are separate from um adjacency matrices. Think of incidence matrices as this. We're going to have all the nodes in the as the columns and in the rows, and each edge is going to have a column. Basically, if a node is on one end of an edge, we'll put a 1, right? And if it isn't, we'll put a 0. And from this graph, we'll basically see that we can represent the entire graph. And one key thing to remember is because each edge only has 2 nodes connected to them. So no column can have more than 2 ones. Is everyone okay with that? I think that's one of the key things you should take away from it, right? Here you'll see, I'll go with the for pseudographs in a bit, but here it's important, right? For every edge that isn't a loop, especially in an undirected graph, every column has to have exactly 2 ones, because no edge can connect more than 2 vertices, and it can't even be less than 2 unless it's a loop like this, right? So for here, where it's a pseudograph, whenever there's loops, you see there's only one, because that edge goes from V1 to V1. Same thing here, E8 goes from V4 to V4. Okay. Any questions so far? After this, we're going to do isomorphism, and I think, unfortunately, that'll be enough for today because it's going to be 5:30, and it's been a long day. I'm going to either take a nap or play some video games. I need to relax. Okay, so let's quickly go over isomorphism, and then we'll do exercise 47. Okay, so the idea of isomorphism is this. If I can have 2 graphs, G1 and G2, they're isomorphic if I can here's like the official definition, if I can map every vertex in V1 to a vertex in V2, such that every vertex connected to a vertex in V1 is maps to the same edge. I'm sorry. Did I explain it wrong? If I can map every vertex in V1 to a vertex in V2, such that every edge connecting to that vertex in V1 maps to the same edges compared, which it maps that I'm speaking in tongues. Let's do the drawing. Basically, think about it like this. If I can take a graph and twist it in some sort of way to get the other graph, that's isomorphic, right? The idea is I want to find a matching such that the correct vertices are correct matched with their respective vertices. Now, it sounds very confusing, but I'll show you what that means. It's very intuitive. Example, I can match U1 to V1. U1 is connected to U2, right? What is V1 connected to? V1 is connected to V3 and V4. So let's let U2 equal V4. Okay. U2 is connected to U4. V4 is connected to V2. So that means V2 has to be equal to V4. U4 has to be equal to V2, or by either vertex. And what that means V1 and V2 are connected to V3. U1 and U4 are connected to U3. So U3 has to equal V3. See how like I matched them in such a way such that the correct colors are matched to the correct colors. Blue with blue is connected to yellow and green. Blue is connected to yellow and green. Brown is connected to yellow and green. I'm sorry. Yeah, brown is connected to yellow and green. Brown is connected to yellow and green. U is connected, green is connected to blue and brown, blue, brown, blue, brown, blue, brown. And thus they're both isomorphic, right? So if you want to see it intuitively, we basically took the first G and twisted it and got H. Okay. In order to see if two graphs are isomorphic, it's difficult-ish. What I would do is kind of like play around. You basically list if it helps, once again, I'm not sure if anyone has like a lot of colors, but it helps like doing something like this where like you color each thing. And if it does help, always start with something. So start with a random matching. U1 maps to V1, right? And then what I saw is from this matching, U2 had to connect to V1. So whatever connects to V1, there has to be one that has to be U2, right? So we did, and then we said V4 is U2. And we go off from there. But in general, it's a bit difficult to see if two graphs are isomorphic right from the get-go. There are some algorithms. Adjacency matrix, or that's also possible. Um, but the reason why I'm saying, I mean, when you do a adjacency matrix, they could look different, but the main idea behind isomorphism is the correlation of vertices. You have to be able to match vertices with each other such that everything else that's connected to those respective vertices like matches everything else. Does that make sense what I just said? It's like I have to match U1 to a vertex here such that later on as I keep matching, I'm not going to end up with a contradiction. Like for example, here U1 isn't connected to brown, blue is not connected to brown. So if I end up here with blue being connected to brown, then I know I went wrong somewhere else. Either they went wrong or they're not isomorphic. Okay. Part rigorous method, part eyeball. When it comes to rigorous method, always remember to count the number of edges, count the number of vertices. If it's ever the case that the number of edges are different, then right off the bat, you know, boom, not isomorphic. Because two isomorphic graphs have to have the same number of edges. There's a couple of strategies. Here's one where you have the adjacency matrices. The reason why I said it's a bit different because um, I think it's a bit, actually, it's not shuffled. Not bad, right? But this only works if you can map them correctly. Well, there's algorithms. So these are like the rigorous methods. There are algorithms for it. They're not the best. So let's quickly do 47 before we finish. What are they asking? What are they asking? Determine whether the given pair is isomorphic. Okay. Oh God, pick the best one for last. Wow. This one is hard to visualize. Okay. Okay. Let's start coloring. While I do this, Daniel, please put the form in the chat. Yeah, when it comes to isomorphism, it's 43. Oh, 43, yeah. Some of them are easy to eyeball. I don't want to lie and say I know a strategy. It's like mostly just experimentation when it comes to these types of questions, trying to like see what matches. For example, we could say U2 is V2. That means U2 is connected with U3, V3. Can you do 48? You want me to do this as well? What the hell? What in the world? Uh, we could try it. I don't know if I'm gonna be able to do it, but so V3, let's say this matches to U3, V4, V4 matches to U4, V4 matches to V9, V9. So this could be U7. What does U7 connect to? V9 goes to V10. Also, I will say another neat strategy you could use is like making sure the edges and like the degrees of each one maps correctly. Like for example, it would be stupid if I did this. Like if I mapped V3, I mean everything I'm trying to map, I have to make sure like I can't map a vertex of degree th of 4 to a vertex of degree 2. Right? So that's like another strategy you could use. I think here, so V10, V6, let's say this is V10, is U10. Um, U10 goes to U1. Nope, wrong color. I'm learning a lot of colors, everyone. I'm learning a lot of colors. U1, V10 can, and U1 also has to connect to that. So let's say that's V8. Okay, and V8 needs to connect, U1 needs to connect to U5. So that's gray. That means V5 is gray. V5 is a gray. U gray, U6. V5 brown, brown. So the other thing, 8. So U6 needs to be connected to V6, U6. Boom. Okay, we're on a roll. Um, how many edges do we have left, everyone? Okay, we got two more. Okay, so V7. This is orange, so that has to be U9 maps to V1 because they're both, yeah, we're cooking, we're cooking. Bingo. And I mean, V7 has a map to V8. Holy smokes, I did not think I was going to be able to do that. But looky here, we did. And it took 2 minutes, 3 minutes. All right, not bad, not bad. If you have colors, then go for it, I guess. It's just, it's think of it as like a little game. That's how I like to think of it. You have to make sure like whatever maps you match it. Like once we got to the ones where it's like you have it's mapped to two different colors, you start seeing like, oh, it has to be that color. Like for example, this purple one, U1, is next to yellow and gray. So that means whatever is purple has to be next to yellow and gray. And if you do that along with other strategies like making sure the degrees of each vertex you're mapping, they're the same and all those, you'll see it ends up being the same and working out. Do you all still want me to do 48 or no? Or you want to, yes, no, maybe we could do a similar strategy and attempt it. Okay. Any other questions? I did not really think that was going to work out, but it ended up working out. Will the recording come out today? And if so, what time? The recording won't come out today. That's a great reminder. The recording itself won't come out today. Let me show you where the recording is going to be. So it's going to be noting the complete subgraphs. Oh, nice. Good job, Ramil. We got, so you want to see a CRU sources. You'll see 220. It should be here. The recording won't be out till Monday because they're off. But what my boss did say is I think some people here did take the recording on their own devices. Discuss with them if you could get it from them as well. And also, I did record it to the cloud and it will go to my boss. So he'll either send it out via email, the recording, to everyone either later today or early tomorrow. Okay, so you're gonna get the Zoom recording hopefully soon, but the actual YouTube video won't be out maybe until Monday. Hopefully that answers the question. Sounds good. Thank you all. Hopefully, and yes, I'll stop sharing. And does anyone have any other questions before I finish the recording? Let me just stop the recording right now. Did I stop the recording? Who stopped the recording? Record? No, what the hell? Oh, stop recording. Bingo.